Hello everybody, in this video we're going to quickly go over a very commonly asked interview question called the minimum window substring. Given a string S and a string T, find the minimum window in S such that it contains all the characters in string T, ideally in time complexity O of n. Let's take this sample input as an example. So one window substring would be ADOBEC, which we can see contains all the characters in T, A, B, and C, which right here are contained within it. However, a smaller substring actually exists, B, A, and C, and the problem asks to return the minimum. So this size of 4 is smaller than the size of 6, so we would return the string B, A, and C. Now we should take a look at some important clarifications we should make with the interviewer before we begin. Let's start by making sure these characters in the input are given in ASCII values, because this severely changes the way we store our characters when we look at our minimum window. Okay, so now that we understand the problem, let's go ahead and explore some options we can take to solve it. Now the first thing we can think of is the naive or brute force solution. And like many substring problems, we can try to generate each possible substring in string S and check if it contains all the characters in string T. So for instance, if we have the string S equal to ABCD, we can check whether or not we can generate all these substrings here, AB, ABC, ABCD, and then BC, BD, and so on and so forth, and then check if it contains all the characters in T, so check each, we want to check each of them, and for the ones that do contain it, we want to find the minimum in that. This approach, as we know, is incredibly slow and obviously has a better solution, but it's still good that we mention it to our interviewer. And since we generate each substring at a certain point, this algorithm will take at least n squared complexity, and it could take an additional complexity in either time or space to determine whether or not our substring is contained in T. So we can either sacrifice more time complexity traversing through T and each substring, or we can use some sort of data structure to alleviate that. But both approaches are still incredibly slow, and a better solution definitely exists. One method you should have in your string manipulation arsenal is the sliding window technique. Sliding window technique, which is essentially very useful for finding substrings with a certain requirement. So in our case, our certain requirement is that the window contain all strings in T. So only after the substring meets that very certain requirement can we check if it's the minimum. And the key observation for a sliding window is that we continuously shift and expand our window to effectively check for the substring to meet our predetermined requirement. So what we have here is a bare template that can be used for all sliding window techniques, inspired from a popular discussion forum on Leetcode. Now let's go over the high-level logic before we dive into applying this specific template to our problem. Now the first thing we want to do is create a bank that holds all the ASCII values in the alphabet and initialize it with a specific string requirements that our substring must have. So in our case, the specific string requirement is that our substring contain all characters in string T. So we can put all the characters in string T into our bank here, and we can do that by simply traversing through all the characters, taking that character, so taking all the characters in string T, so let's say that we have character T in string T, and we simply increment it to represent that our bank includes it. So after that, we have 2 pointers indicating the boundaries of the substring, indicated right here. And so for example, let's say the left pointer was equal to 0 and the right pointer was equal to 2, and we have the string A, B, and C, then our pointers would represent this entire string because string C is index 2 and the left index is index 0. So these indices are inclusive. They're inclusive. And we also have a counter to give us a numerical check of how many characters our string or our sliding window has of this string T. And we can actually use this pointer as a conditional for determining if our substring meets our requirement of containing all those strings in T. So right here, we would actually check for that condition. And in this specific problem, the condition would be that counter be equal to T dot length. If this condition is the case, and the counter represents the number of characters that our substring has of character or of string T, then if they equal each other, our substring contains all the characters in string T. And we also want to make sure that our window is expanded at least until the end to include all the possible characters, which is what this conditional check does right here. So as long as our end or our right pointer is less than our string size, we want to keep expanding. Keep expanding. Now, we also want to continuously shift our window or expand our window when all our requirements aren't met. So actually, I should clarify what these words are before I dive too deep in them. Expand. What I'm referring to when I say expand is increasing the size of the right pointer. So if we have right equals 2, then we make it 3. So we basically shift it this way. Whereas shifting, when I say shift, we take this left pointer and we move it 1 to the right. So it's basically making our window smaller. Now, we want to, so once the condition is met, so once counter is equal to T.length, only here can we check whether or not this substring is a min. So in this body right here, we can finally check if our substring is a min, is our min substring that meets these requirements. Now, once we've done this, we need to start de-incrementing. We need to start shifting our window by incrementing the left pointer. So that's what this left pointer incrementation does. And we want to give back the character represented by it. So this essentially removes our sliding window's reference to that character, and we give it back here. So actually, I believe I skipped over this part right here. So when we shift our window right here, we expand the right pointer, so we increase it by 1. However, we also de-increment that point in our bank. And what happens when we de-increment the point in our bank is that we basically say, oh, this is accounted for, this character is accounted for. So the entire bank would have characters, would have frequencies for every character less than or equal to 0 when this condition is met. And so when we shift our window, so when we're no longer representing that character, we need to give the character back. So I'll give it a quick example here, and I'll also go over another example once we actually implement this algorithm. So let's say we have S equaling A, B, and C, and T equaling, let's just say B and C. And our window is representing the entire string S. So we have left equaling 0 and right equaling 2. Our current bank would actually, so if we look at our current bank, and I'll actually switch colors just to make it more clear, our bank would actually have A as -1, B as 0, C as 0 now, and every other character in ASCII as 0 because they haven't been encountered, but they don't exist in T. So initially this bank would have C and B as 1, but since we've seen these characters here, they've been decreased by 1, and we've seen this A here, so we've gone ahead and de-incremented A by 1, so now it becomes negative. We see that, oh, the condition is met because our counter is now equal to 2. We've represented all the characters, both characters in T, So now we check whether or not ABC is our min, and then we want to evoke this piece of code right here, which shifts our window. So we can see, from our point of view, we can see that, oh, A is probably unnecessary, but the algorithm doesn't know that. So all it does is it continuously shifts the window until the condition is no longer met. So let's go ahead and shift this window one to the right. So this is what this begin does. So we shift this one to the right, and we give this A back to the bank. So now, by incrementing it, this A becomes 0 again. Now, let's apply our sliding window template to this specific problem. And we have our code right here. So as I mentioned before, our substring condition is to contain all the characters in string T. So we want our bank to track all of our characters in T, and we can do this by initializing it with all those characters. So that's actually what this line does here, and like what I mentioned before, to initialize it, we simply increment the ASCII value associated with each of those T characters. So when we stick this in the array index, we're actually just getting its ASCII value, and the represented ASCII value is increased by 1 here. It's also a good habit to check and mention our edge cases in this problem as well, which I have up here. So we know that if our either string is null, or if either string has a length of 0, we should return an empty string because no solution really exists. Now when T is 0 and S isn't 0, we still have an empty string because no matter what our substring is, it's actually the absolute minimum since T has no characters. And one additional edge case, which is actually handled by our other code but is interesting to mention, is if T.length is greater than S.length. In this case, we see that no substring within S actually exists, which contains all characters T, since T is actually larger. Now we've got all these same variables here, so we have our bank with 256 ASCII values. We also have a left and right counter, and we also have a count right here, which, like what I mentioned before, represents how many characters our current substring window contains of string T. Now, when we expand our window, so let's take a look at the code right here. So when we actually expand our window, we increment the right pointer, and we simultaneously de-increment it to indicate that this character has been represented in our sliding window and we no longer need to keep it in our bank. And if this de-incrementation before it's de-incremented was larger than 0, then we know that it was in our string T. Because when we initialize our bank array, so let's say T is equal to A and B, we make these frequencies 1 and B equal to 1, and everything else is equal to 0. So we know that it's existing in T because it's greater than 0. We see here and here represented in T. And so before we de-increment, we check if it's greater than or equal to 0. If it is, then we iterate our count. Now, the next body is the case when our condition is met. So this body right here, our condition is met such that the sliding window contains all the characters in string T, as indicated by our counter being equal to the length of T, indicating that our window has all the characters in T. So our condition is met. Condition met. Okay. And finally, because our substring is valid, we can finally check if it's a minimum relative to other valid substrings. And we can do that by simply checking if right minus left, which indicates the current window size is smaller than min. If it is, then we update accordingly, as well as our min string. Now, we want to be a little careful with our pointers here. So the only reason we can do just right minus left and not include a +1 is because we've already incremented right here. So generally we have to add a 1 to account for the fact that we're starting at 0, but since we're always continuously shifting our window, our right pointer is always one ahead of our window. So if, for example, here we have our right pointer here and our left pointer here, A is actually the only character currently in our string because the moment right added in A, it was incremented without adding in this B. So we've actually already accounted for this +1, and you just want to be a little careful when you're writing your code that you don't have to add the +1. Now, in order to break out of this conditional, we need to start shifting our window. Because the minimum substring started from the left index of this window, we've checked all these substrings which are valid starting at this left pointer thoroughly, meaning that no shifting of the window will actually get us a better solution. So basically the left to right window, if it's valid, has given us our best solution starting at the left pointer. So it would be moot at this point to continue checking and expanding our window. Now we can shift our window until the condition that count is equal to t.length is no longer met. So we keep shifting our window and we keep ignoring the case where we shave off irrelevant characters. For instance, if we have the window ABC, S equaling ABC, and T is equal to C, and our window completely inclusive is A, B, and C, so I guess our right pointer would be here, then when we shave off, so when we increment left and we shave off this A, it doesn't actually change the fact that it doesn't actually affect our count because A wasn't included in T anyway. And this is actually sort of the heart of our solution, because once we've reached the end, we can continue shaving off our solution and making our solution better until it's no longer valid, and then we continue expanding our window at the new left point. Now let's go over how this process of shifting works. So like what I just mentioned, we need to give back the character that we're iterating over, that we're shifting over. So when we increment left, there was a character represented by left, which is no longer represented in our substring. And we need to account for this. To account for this, we need to give the character back by incrementing the respective frequency in the bank. This left here is basically shifting our window. And after we give it back, if the frequency is greater than 0, we know that it was originally in our T. So we give it back first, then we check if it was greater than 0. And in this case, if it existed in T before, then we can decrement count to finally break out of this loop right here. And that is the heart of our algorithm. So after doing all that, we can finally return what our respective solution is, which is the min string associated with the minimum count. All right, so now that we understand the question, let's go ahead and go over an example problem and visualize each step involved. So given this input, S equals ACBA and T equals A and B, we'll go ahead and see what each variable initially looks like and traverse through each of the steps, understanding what the variables look like at each step and where the pointers exist. So initially, because we initialize our bank with all the characters in T, our bank will actually, so first thing to understand is our bank actually contains each ASCII value, and each ASCII value has a frequency. For the purposes of this representation, oops, wrong character there. For the purpose of this representation, we'll go ahead and just say the actual character instead of the ASCII value. So here we'll have A represented, which would actually be an ASCII value of 0. In this case, it'll be 1. B's in here as well. It's 1 as well, and it's this. And 0 and 1 are actually lowercase characters. So I guess this would be a little different, but C would equal 0, and all the other characters in the ASCII chart would be 0. Our min is initialized as the max possible integer. because we want it, if a window exists, to replace it immediately, no matter what. Our current string is empty, and our left, right, and count pointers or variables all are 0 for now. The window is currently nothing, and our count is 0 because our window does not represent any characters in T. So currently our 2 pointers, we'll use blue as our right pointer and green as our left. Both are pointing at A. And the first step is to add or increment the right pointer by 1. And before we do that, we need to de-increment its representation in the bank. So at character A, we need to de-increment it. So now this 1 becomes 0. So we'll actually visualize this in the next step. So A is now 0. We've de-incremented it. B remains the same, as well as all the other characters. Our min remains max int because a legitimate window hasn't been reached yet. Current string similar. Left pointer is 0. Right pointer is now 1 because we've incremented it, and count is now 1 because A is actually in T. So we'll go ahead and increment that. Okay, so next, and let's make the pointers as well. So we have that and that. Okay, so now let's do the same thing with our next pointer at the right. So our bank, if we de-increment C, is now A equals 0, B equals 1, C now equals -1, and so on and so forth. We still have to de-increment C, even though it's not part of our T, because we still need to keep track of what characters are actually in our character bank and what characters are being represented in our window. So min remains unchanged at max int. Current string is unchanged. Left is 0, and now right is 2. And our count, since C wasn't part of T, is still 1. Okay, and now the right pointer is pointing at B. The left pointer is still at A. Okay, for the next question, or next part. So B is de-incremented, so now A is 0, B is 0, C is -1, and wow, look at this. Our count is now 2, which is equal to the length of T. So now we need to update our min and current string, and our min is updated with right minus left, given that right has been iterated. So right is now, let me make this very clear, right is now, it's a mistake. Right is now at A, which is pointer number 3. Left is there, so right minus left is 3, making our min 3, which is smaller than infinite, of course. Our current string is the right character -1 to the left pointer being inclusive, so now it's A, C, B. Our left pointer is currently 0, right pointer is now 3, and our count is 2. Okay, so we've reached a point where count is equal to the length of T. Now we need to trigger our window shifting part of the code. So now we increment left. Now we'll increment left because we're shifting it, and the character at left is no longer represented in our window. So now left is at C. Our right pointer is unchanged, and our bank has given A back. So now A is 1. B is still 0 because it's still represented, and C is still -1. And we actually know that the character A was represented because it was at least 0. So this is at least 0. So now count is now 1. Right is still 3. Left is now 1. Current string remains as is, and our min remains as is. Okay, so now that our count is no longer equal to 2, which is the size of T, we can go ahead and expand our window once more. So now we go ahead and de-increment A. So our bank is now A equal to 0, B equal to 0, and C equal to -1. our right pointer is now sort of off the charts, and be aware that this will now actually break our outer while loop condition, being that right is less than the length of s. However, there's still another condition we have to satisfy. We have to satisfy the rest of this while condition. So our algorithm is not finished quite yet. Our left pointer is still pointing at C. Our count is now 2. Count equaling 2 triggers a min and current string update, check. So our right is now equal to 4, and our left is now equal to 1. So that so the min is still 3, which is equal to our old solution. So we'll go ahead and leave it as is, and we'll go ahead and leave our old one in because it doesn't really matter right now. So now our left is 1 and our right is 4. So like I mentioned before, our right is now equal to the length, which actually breaks our while condition. However, because our count is equal to 2, it actually triggers this inner for loop here, which says while count equal to length of t, continue this while loop. So now we need to shift our window, and since this is our last window check, all we need to do is shift our window to the minimum point and we have our solution. So let's increment C and check that again. So let's increment C. So now A is 0, B is 0, C is now 0. Note that the old C was -1, not 0, so C is actually not part of our T, and that's good. Our count is still 2. Our min with our right pointer at 4 and our left pointer now at B is actually equal to 2. Right minus left, 4 minus 2 is now 2. And our current string is now BA. Our left pointer is now at 2, right pointer is at 4, and we break out of this loop. Oh, actually, no, I'm actually wrong about that. So this, oops, it's okay. This count is still not meeting the condition. So we actually still need to shift our window until that maximum is broken. And even though we know that this is the best possible solution, it's actually not obvious to the algorithm unless we build in a check, which checks if our min is equal to our the size of t, which is the smallest possible solution, then we can break. But this is sort of too specific, and we should still follow the algorithm that we've defined. So now that we have an extra step, ACBA, our right pointer is here. We go ahead and iterate the left pointer, so now the left pointer is at A. Our bank, wow, the different colors now. Our bank is now A being 0, B equaling 1, so we've given B back, and C is still 0. Our min is unchanged because our count is now 1, which breaks the for loop, which breaks the while loop. So now this min isn't even checked because the window isn't actually valid anymore. So now we can stop our algorithm. And there's actually one last thing that I haven't mentioned yet, which we need to check for, and that's what if no valid sliding window actually exists. So for example, if in our algorithm here, say ACBA, so ACBA, if we actually just took this B out and T is equal to AB, there's actually no valid sliding window, because no matter what window we make, we don't have the B. So how do we know this, and how do we check for this? Because it'll simply return current string. And in our specific approach, returning empty brackets is actually okay. We have to clarify this with the interviewer. Sometimes they might want us to return null or something. But in this particular implementation, because we have a current string, we actually don't need to do anything additional. However, some algorithms actually try to take advantage of the left and right pointers and simply create a substring. And in that case, we actually need to be a little more careful. Alright, I just wanted to end this video by pointing out some mistake hotspots and to thank you for watching. I hope you've learned this algorithm, and I hope you really understand this minimum window substring problem as well as the sliding window technique. So the first hotspot I would recommend you really be careful at is to decrement after you check if it's greater than 0. So this line of code right here, so we want to make sure that before we take the variable into account, the character into account, we check if it's greater than 0. If it is, then we know that it's contained in t. Similarly here, we want to be careful with the right minus left pointers, like what I mentioned in the video. Because we've already incremented right, we can just do right minus left without adding 1. So that plus 1 from this part right here, because it always gets added by 1 in this particular piece of logic, we can just do right minus left. But if you decide to do right plus plus in this, or I guess that would be incorrect, but if you decide to do it afterwards, or if you don't decide to increment it for some reason, then you would have to add a 1 to account for the array starting at 0. And perhaps the most tricky problem here is to take into account that we need to add, or we need to increment before we check if it's greater than 0. So we need to give the character back, then check if it was greater than 0, because only then do we know that it was contained in t. So if you were to increment after you check, then you would need to make sure you check if it's greater than or equal to 0. So that's what I have for this video, and I will see you in the next one. Thanks for watching.